Whoops. That should work. All right, let's go ahead and get started. All right, guys. So everybody that's online, welcome. Jose, and then everybody else who will be coming. Welcome, guys. Today we're going to be doing the ASE A8 test review. Just like with yesterday, we did the A6. So today we're going to make sure we cover the A8 portion, engine performance. I've noticed that a lot of techs, I don't know if you guys seen this, but a lot of techs have been complaining, or not complaining, but not understanding what engine performance really is. And as a diagnostician, we need to understand engine performance, how the engine operates, computerized systems, ignition, all that fun stuff. So this way we have a better idea of how to diag a car, and at the same time get the ASE, which is going to help us look better and increase our value, right? So just like we talked about yesterday, in all of the US, according to ASE, there is 173,213 techs who have some sort of ASE. They can have one, two, or many other. And cool. So Timothy, congratulations, man. So we had an A6 pass. So congrats, bro. Congratulations. If you guys have any questions about this small class, make sure you guys put them in the chat. I am running solo, so I'll be running back and forth to the computer to look at any comments, and then I'll go ahead and answer them for you guys as we go along. Right now, there's only Jose here in person, but somebody else comes in, and we can add to that as well. So don't be afraid to ask questions. All right. According to ASE, there's only about 63,618 master technicians. Just like I was mentioning yesterday, that's the goal. And one of the reasons why you want to get master level status is not only because you get a cool gold patch, but this is going to tell you where you're at on different categories and what you need to brush up on, right? So getting that status is going to help you understand where your weaknesses are, kind of brush up on them. Obviously, if it's not your specialty, well, then don't really focus a lot on it, but you still want to know some of that part. Okay. So as of ASE, this is what we have so far from A1 through A8. These are the amount of technicians that we have. When we look at engine performance, there's only 98,103. So that number is actually pretty low in comparison to everybody else, except for automatic transmissions, which I'll be honest with you guys, I had a hell of a time passing automatic trans. If it wasn't for James Halderman's automotive transmissions book, I would not have gotten through that one. And Travis is saying that you get a gold magnet from ASE, which is true. And then you also get another magnet, or what they call it, a toolbox medallion, every time you pass or recertify an ASE. So it's pretty cool. According to ASE, right now we only have L1 status, 30,000 techs. For the L2, 3,000, and hybrid, 1,500. This hybrid one, with what the government's imposing, it's a good idea to go ahead and get it now. That's going to help you guys when it comes time to start working on more EVs. Get ahead of it and get certified within it. So here's what the ASE test is made up for the ASE engine performance. We're going to do general diag. That's 24% of the actual test. Ignition system diag is 16%. Fuel, air, and exhaust is 18%. Emission system diag is 16%. And computerized controls is 26%. Now, the one that most people get upset about is D, emission systems, because some people say, well, I'm not in an emission state. I understand that, but at the same time, some of these emission systems can actually cause drivability problems. So we need to know how they work. If one thing that my mentor told me, and I pass this along, is if we understand how a system works, we can fix it. If we don't know how it works, then how the hell are we going to fix it? So by understanding how it works, even though we're not in an emission state, we can definitely help out when it comes to a drivability problem. Okay, so we're going to cover all of these today in a brief review. I got about 90 slides we're going to cover. It's 6:35 California time, so I'm shooting for about 8:30 completion time. We might go a little bit over like we did yesterday, but try to get everything in there. Let's start with general diag. One of the things when it comes to general diagnosis is we need to start with asking questions, right? Like I was talking about yesterday, what happens is a lot of techs just get so deep into their thought process, they forget to ask. Most important thing is ask the owner or the driver of the car. They have so much information about what's happening with the car, what problems are going on, that if we just talk to them, most of the time they do most of the hard work for us, right? Being able to communicate that to the customer is going to make our jobs that much easier. Step number 2 is know the system. So if I'm trying to diagnose an evap system, for example, but I have no idea how it works, how am I going to fix it? Right? So usually that's why a lot of techs and shops end up throwing parts at something, because they don't know how the system works. And the crazy part is the majority of systems are almost the same. They just change, tweak little things here and there, or how they observe the operation of the actual system. Number 3 would be to operate the system. If we're dealing with like an evap system, sometimes we can do a service bay test where we can use our scan tool to force to run the actual evap test. If it fails, we'll get a code for it. If it passes, it passes. So we know that the system's fine. Not all manufacturers have that, but the ones that do make it so much easier for us, because all we have to do is press a button, sit down, chill, and let the car run its course. The other thing is list the possible causes. Well, if I have a car that comes in and has an evap leak, right, and it's a small leak, then I start thinking, what can cause a small leak? It could be a gas cap, it could be a purge valve that might have some charcoal or carbon buildup in it that's not sealing properly. We've seen spiders, spider webs, mud, rocks in vent solenoids, stuff like that can cause those types of problems. Now, if we get a car that has a large leak, right, and we interviewed the customer during the interview process, customer says, well, I just had a fuel pump replaced. Well, now I'm thinking, all right, probably somebody screwed up on the O-ring. I'm probably gonna have to drop the gas tank, right? So we have to make an assumption of where I'm going to be headed and what kind of test I can actually run. So you want to isolate the problem area, try to figure out where can I reduce this from an entire car to a section, right? That's what we want to do as a tech. One of the biggest problems I see with a lot of technicians is they try to diagnose the whole car. But in reality, we're not diagging the whole car. We're diagnosing a smaller section of it. So we want to take that 16 feet of car, reduce it to a small section, right? After that, we want to know where the problem area is. Then we're going to run some tests, right? If it's an evap test or an evap leak, smoke machine at that point. Put a couple of drops of some dye in there, helps us with the UV flashlight, pinpoint them a little bit better. And then we can use a smoke machine, and most smoke machines have a flow gauge, which tells us how large the leak is. Okay. After we figure out what's wrong with it, we sell repair. If we do the repair, then we're going to verify it, right? We want to verify our findings, do the repair, and then retest it just to make sure we actually completed it. Now, one thing that I've been noticing with some of the states that I've gone to teach that don't do emissions is they don't follow through with number 10. And the reason why is they always say, well, we're not an emission state, so monitors don't matter here. I understand that, but if I can get the readiness monitor to flip from incomplete to complete, what is that telling us, right? What do you think that tells you? System's fine, yeah, right? As long as it flips from incomplete to complete, but there's no check engine light or no pending code, we fixed it. But what happens is a lot of shops just get that in their mind. Oh, I'm not an emission state, so I don't care about it. Run the monitor. If we can get that monitor to run, if your repair was successful, we're going to be in the clear, right? So that's always one thing we want to make sure, and we want to follow through with that. Most shops, that's where they drop the ball on number 10. The person who actually verifies our repair is the customer, right? Can you imagine a customer comes in, pays you a couple hundred, maybe $1,000 to fix their car. They take off, 20 minutes later, check engine light's back on, right? They're going to come back, they're not going to be happy. Why? Because they just paid you to fix something, and what ended up happening is you supposedly fixed it, but because you didn't test drive it, what's up? They verified your repair. They verified your work. That's not who you want verifying your work. Because always remember, if for some reason we drop the ball, we still have possession of the keys, right? They don't have them. So at that point, we can still try to do something to patch that car before we ship it down the road. Okay, so that's why I always talk about making sure we verify a repair. When it comes time to diag, always remember there's two different things. There's a concern and a complaint. There's a difference, right? When it comes to being a concern, that would be something that interests you because it's important or affects you. The check engine light is on with a rough idle. That is a concern, right? We got a mill on. and we got a rough idle. Now, if it's a complaint, that was basically an objection to something that's unfair, unacceptable, or otherwise not up to normal standard. What if the customer just went from a Toyota Prius to a Toyota Tacoma, right, with some heavy off-road wheels, and it's humming? And they come to you and they're like, dude, my car, I have this complaint because my car hums as I drive, right? You go outside, you look at it, it's like, dude, you're running mud terrain tires. How are you not going to hum, right? That's when our job is to let them know that that's normal. That's just your car's different than the previous one, right? I don't know if you've had this, but we've seen this before where especially the older generation will have a car that they were so used to for the past 10, 15 years that when they upgrade to something else, they don't have the features they had 10 years ago. So they're going to come to the shop and be like, oh, my car's doing this. Well, that's normal, right? It's like if somebody comes in and says, hey, I don't have a cassette player. Like, dude, you're a little bit far behind on technology, okay? Right? Got a guy whose vehicles don't even leave the parking lot most of the time. Yeah, absolutely. I make a joke of it, but this is very true. I know a lot of shops that their test drive is from the bay to the parking stall, right? They're going to pull it out, park it, take the keys right into the front office, and then ship it. That's a big problem, and that's the reason why we end up in some situations, okay? We had a vehicle in today that I posted this on Facebook, and customer was complaining of a check engine light with a rough idle misfire, and we found it was timing chains. So when we presented the RO or the estimate to the customer, he was kind of upset, and he started kind of going off on us, but it wasn't more towards us. It was more like he was mad, but he was mad at the previous situation. So he had gone to some other shops and the usual through plugs, coils, and stuff at the car. Once we got it, that's when we figured out timing chain issue. So we sold them timing chains. And throughout the whole process, I mean, most of the time we could be, some shop owners and shops could be like kind of dicks about it. But we were just like, all right, it is what it is, man. We're not taking it personal. About 2-3 hours later, he comes back, drops deposit down, leaves the vehicle. So now we have a customer out of it, right? So it's just basically being able to explain to the customer what you found, show them pictures, show them videos, show them proof, and they'll pay, right? And he saw how we were different in the previous shops he was working with, and that helped out the whole situation. Okay. My thing is always start with the basics. I can't stress this enough. Start with the basics, man. Start with the basics. State of charge of the battery, 12.6 is 100%. If we got 12 volts, it's dead, right? We've had some cars in here. We had one not too long ago where Jose's not here for it, but it was hilarious. It came in with a bunch of codes. And what was funny is that most of the codes in every module said low voltage. And the reason why it came to us is the shop that had it was trying to sell them a DME, a computer, right? So we're not really a big European shop. We're like, all right, well, we'll check it. We didn't understand why they decided on the DME, even though all the other modules said low voltage, right? We just ran an oscilloscope test on the battery and it failed. We sold them a battery. That was a fix, right? We sold them a battery. So this is why it's important that we start with the basics. And you'd be surprised how many techs skip the basics, right? You get a car that comes in with a P0101 mass airflow, go check the air filter. What if the air filter is clogged or non-existent, right? Or like you've seen on some social media posts where it's still in the bag, okay? There's all kinds of stuff, but we got to start with the basics. The basics are going to help us out a lot, right? Like we were talking about yesterday here, some of the voltage drops that we see commonly used. If we're on a ground circuit, it should be about 200 millivolts or less. Yes, there's different publications that say different, but this is the more generic number that we all kind of live off of. Voltage drop from battery positive to starters, 300 millivolts. Battery positive to alternators, 300. Battery post to terminal is 200. And then across the starter solenoid is another 200 millivolts. So this is something we need to memorize because you'll also see it on the A8. So if you take the A8, not only is this on the A6, it's going to be on the A8, and it's definitely going to be on the L1. So when you take your L1, you're going to see it again. Which, again, as a automotive tech, especially a diagnostician, this should be something that we already know off the top of our head, right? This is one of those things we don't have to go back and look up. This is not something we should have written down. We didn't have it up here, right? Because if I'm already hot going in there on a diag and there's like, oh shit, what was that voltage drop again? So then I got to leave what I'm doing, go back to my box, pull a folder out, kind of go through my notes. It's not pleasant. So this is something we want to already know. From there, this is a very important test. One thing that I always still do to this day, besides a relative compression test, if I get a car that comes in with a misfire, first thing I'm going to do is pull my vacuum gauge. Vacuum gauge is one of the best tools we can use when it comes to general engine status. See how the engine's doing. Back in the old days, on the carbureted days, we used to use them a lot. Okay, it's funny because I'm only 35. A lot of people, and I make fun of us old farts because I got to work on carburetors, and carburation was actually pretty cool because we could use a vacuum gauge to get optimal engine vacuum based off of carburetor adjustment, right? So we would use that quite a bit. What we want to do is anytime you're going to use a vacuum gauge, easiest thing you could do is find your purge valve, because the purge valve is going to be in a centralized location because it has to distribute hydrocarbons, right, or fuel vapors. If I put that purge valve close to cylinder 1, 2, 3, or 4, we can have one or more cylinders that are running excessively rich. So what we want to do is we want to put in a central point where it's going to evenly distribute between all cylinders, right? So that would be your best point to actually put a vacuum gauge. With the engine at idle, you should be about 18 to 22 inches or 17 to 21 inches, depending on what book you're reading. There's 2 different variations, so it all depends what you're actually looking at, and that'll be able to help you, right? Somebody just said, what's a vacuum gauge? Use a pulse sensor. Definitely we can use a pulse sensor. For the ASC, though, we're going to be using a vacuum gauge. Always remember that for every 1 inch, or excuse me, every 1,000 feet of elevation, you lose 1 inch of vacuum. Here in Rancho, we're about 1,400 feet elevation, so typically we kind of round it off to 2. So we're going to have 2 inches less. So instead of 18 to 22, it's going to be 16 to 20. And when was it? About last week, we were testing a car. It was about 19 inches. So it's right there. We always want to make sure that we have a steady needle. Okay. And this is actually a tip that I tell a lot of my students and people I know. If you're going to go buy a used car, take a vacuum gauge with you. Vacuum gauge and a scan tool. Because with those 2 things, what are you going to be able to find? You're going to be able to see if I have good, steady engine vacuum, engine integrity is fine, right? And then if I have all monitors complete, then I know they didn't just clear the check engine. So I have a better understanding that I'm not buying a lemon. I'm buying something that's pretty decent. Okay. So this is going to come up on the A8 where they're going to give you vacuum gauge readings like you see here. When you see a vacuum gauge reading that's dropping about 1 inch, and usually you might see a bounce in the needle, that 1 inch variation typically indicates a valve seating problem. So if you see a 1 inch variation on your gauge, then now we know for sure that this is going to be a valve seating problem. On this one, if we have a vibration where we see the needle jumping back and forth, then that's how we know it's valve guides. So if you see a needle jumping back and forth about 1 to 2 inches, doing this pretty rapidly, you know it's going to be worn valve guides. So at that point, you can follow that up with a compression test or a leak down test, but you got valve guide issues at that point, so we need to recommend a valve job. This way, that's going to take care of that concern, and all we did was use a vacuum gauge. This is why this tool is freaking awesome. If you have a vacuum leak, what you're going to be seeing is you're going to see vacuum gauge dropping to roughly about 3 to 9 inches. It's going to be bouncing back and forth. So that's going to indicate you got a vacuum leak, right? Typically, when we have a vacuum leak, we're going to be able to hear it. Sometimes we don't. So using a vacuum gauge can actually help out with that. Okay, so we got a question here. It says, random question. What does it mean when you pump the brake pedal, RPMs slightly go up? Does that mean you are losing or giving vacuum? So typically when you're applying the brake pedal, we have a diaphragm that has vacuum on one side, positive pressure on the other. So the vacuum is pulling the diaphragm as you apply the brake pedal, then that's going to help us move the diaphragm forward. So we do have a slight loss of vacuum. Thus, we have that small little increase in RPM, and then that'll take care of that. Let's see. We've got another one, fuel trim data or for vacuum leak. So we have a vacuum leak. This is typically what it's going to look like. You can confirm that with your long-term fuel trim. One thing I like to do if I think I have a vacuum leak, and I don't know if you've done this before, but if you think you have a vacuum leak, just raise the RPM. Right? So I'm going to look at my short-term fuel trim, and I'm going to raise RPM to about 2,500. If my short-term fuel trim begins to shift towards the 0 point, then I know I have a vacuum leak, right? Because with the engine running a lot faster, what's going to end up happening is the events happen at such a fast pace that all that extra air coming in is getting blended in with the fuel that's being commanded because of the incoming air. So by doing so, we can really tell off the bat if you got a vacuum leak, right? The other way is if we have a car that has a idle air control valve, which we're going to talk about in a little bit, you can look at the IAC counts. So when we get there, I'll remind you guys on that one. And then this one right here, this would be a valve spring problem. What you want to do is you want to raise the RPM about 2,000 or 2,500 RPM. And if your gauge begins to back and forth, you got a valve spring issue. The other way you can follow this up, right now when we get to ignition, you can see if you have a valve spring problem by looking at your secondary ignition waveform. So by either connecting your scope directly to the coil or spark plug wire or using a paddle probe, you'll be able to see if you got that. All right, so it's pretty cool by looking at your secondary ignition. And I'm a firm believer in testing it multiple ways to confirm that it's really the fault, right? If I run this test and I see that it's bouncing back and forth at 2,000 or 2,500 RPM, I can suspect it's a valve spring problem, right? Now my next thing would be to follow that up with secondary ignition. If I do a secondary ignition and I can see it on my KV, boom, we put that together and now we have a confirmed repair that we can actually sell to the customer. The cursed P0171. Right? Okay, if we have a restricted exhaust, typically what's going to end up happening, we can bring RPM up and then you're going to see that needle just start bouncing all over the place. Typically also going to be associated with lack of power during acceleration, right? So a lot of times when we have restricted exhaust, customers complain like, dude, I'm gunning it. My car's like, whoa, 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 barely taking off. And then finally when it takes off, then it'll go. Or the customer will complain about, I have to apply the throttle slowly so the car can take off. And that's usually just referring to you got a restricted exhaust, which typically is going to be within the cat.
Well, what caused that to begin with?
So if you have a cat that plugged up, typically a car that ran with a misfire for a while or excessive fuel consumption melted the crap out of the internal element. And when that happens, that substrate's gone. So it just melts together like a giant wand. So air can't flow through it. When air can't flow through it, then it gets plugged up, adds back pressure to the engine, vacuum drops within the engine. So it just becomes a nightmare. And that where it gets worse is when you have an engine that has multiple cats. So I got a question. Is a brake booster line also a good place to check for vacuum? One of the reasons why I don't recommend using the brake booster hose is we've tested cars that have check valves. And what happens, the check valve acts like a shock absorber. So if we have any dropout in vacuum, it looks perfect. That's because of the stupid check valve. Yeah. So this hasn't happened to me, but good friend of mine was telling me he had a situation where he ran a vacuum test on a particular Honda, and when he connected to the brake booster hose, that brake booster hose was only off of 2, not 4 cylinders. So when you were looking at it, it looked freaking wonky, and that was only because it was feeding off of 2 cylinders, not 4. So we got to be careful whenever we use the brake booster hose. One of the other things that's important whenever we're doing a basic drivability diag is relative compression. What I'm doing here with my oscilloscope is I connected my amp probe to my actual car on the negative side of the battery. I disabled the ignition and then I began to crank it. While I'm cranking it, what we're looking at is all of these individual humps here. This is your starter, right? This is current draw. Every time we have a peak, what's happening there? So let's kind of analyze that. As the starter's rotating, right, it's going to need more current to overcome more pressure, right? would you agree that each one of those peaks is representative to compression?
Yes.
Right? So as we notice, as the piston's coming up, it has to compress air and fuel. As it's doing that, it has to work harder to do it. That's why we have an increase in current. If we see that there's one of these humps that keeps dropping out and then it repeats, then it repeats, then it repeats, we know for sure we got one or more cylinders that's low in compression. So this is a good way for you to verify if you have a mechanical problem on top of using your vacuum gauge, right? When we get a car that comes into the shop, anytime it has a misfire, we run this test as well. All we do is connect across the battery, because part of our diag is we check the battery and charging system. By doing so, we're going to see how the battery is doing, how everything else. Then when we run this relative compression test and we see that we have a dead hole that keeps repeating and repeating, then I know I'm going to chase a mechanical problem, right? A lot of times you have technicians who start with coils, plugs, and all that stuff, but they skip the mechanical part. So this is why running this test can get me into that area really quickly to kind of have an idea, is this a mechanical problem, a fuel problem, or an ignition problem? Because that's what I need to do quick, right? Especially if you're at a shop that's plays you flag hours and you got 1 hour to diag it, you got to be quick. And how you're going to be quick is you got to determine, is this mechanical, ignition, or fuel? Quick. So this way you can go, cool, it's mechanical. Boom, let's jump into mechanical testing, right? It's fuel. Let's jump into fuel testing. It's ignition. Let's go into ignition. And that's how we play it when it comes to diag, because it could only be one of those three things, right?
Question.
Yes, sir.
Each of those humps,
Mhm.
do those represent each time it starts drawing current, or are those? Like
Yes.
Oh, okay.
So each one of these humps is start a current draw, each peak, but at the same time, each one of these peaks is actually compression with each individual cylinder.
Okay.
Yeah.
So is it one? So if
So-
it's a V6, the first six is the first.
Not necessarily. If this is how I run it, if I'm gonna do a general check, I'll run it like this, right? But then if I want to pinpoint which cylinder it is, then I'm gonna synchronize off one ignition coil. And then from there, I'll follow my firing order, and then it'll keep repeating, right? Because it keeps repeating.
Yeah.
So then now, let's say if I go off of number one, it's a 4-cylinder. So every time I see my ignition event, then from there it's 1, 3, 4, and 2. Then 1, 3, 4, and 2. So that's how we're able to determine which cylinder it is.
Okay.
So anytime you're going to be doing a relative compression test and you want to know which cylinder is the one that's having the problem, what you want to do is you want to create a sink. Don't use a fuel injector, because a fuel injector is not at top dead center. It's before. So it's going to throw you way off.
Okay.
So you want to use the ignition coil, because the ignition coil should be firing relatively close to top dead center.
Yeah.
Right?
Okay, makes sense.
Okay. But I don't add the ignition until I see that there's a dead hole. If I see one of these humps it's missing, then it's missing again, then it's missing again, then it's missing again, then I'll add the sink. Right? Why? Adding the sink takes a little bit longer, and I'm trying to go quick.
Yeah.
Right? So if I set this up and it looks flat like this picture right here, I'm moving on. But if I see that one gap, then I'm going to go set up the sink, because I need to know which cylinder it is, right? Okay. I actually borrowed this from Scanner Danner. Let me turn it on, see if you can hear it. And then I'll mute that in a little bit.
Keep tracking. Keep tracking. All right, that's good.
Okay, so pause. All right, so you heard how that was sounding repetitive. Da, 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 da. So when we're doing a test on a car that you think might be a misfire, this is one of the things we do. When we go out to the car, we'll just crank it, right? I've been called out to so many cars to diag, or cars have been brought to us, that when we start cranking and we don't hear that da 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 da. It's like, dude, are you serious? Like, you didn't hear that, right? So you want to look for a good engine cadence. Each cylinder has to be contributing well enough that you don't have a problem. So it should be da 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 da, right? So now let me show you one that has a problem. Okay, so we can hear that difference. We can hear that going da 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 da, right? Every time it does that gap or that longer crank, or that faster crank, I'm sorry, is because we have low compression. This is how easy it is to pinpoint, is this a mechanical problem or not, right? The engine sounds different. I remember when I was learning, we had a car that came in with a timing belt that went out, and I went to go crank it, and it sounded weird, right? And I had never seen this before. I was 18 years old when this happened. So I went to go ask one of the other guys, and I was like, dude, listen to this. And he just starts laughing. He's like, dude, that timing belt's gone. That engine's gone. Okay, so you want to make sure. What's up, Rico? Nah, you're good, bro. So you want to make sure that whenever you're running these types of tests, this is super simple, right? All we have to do is just listen to it, and if we have that constant ta 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 ta, we know we have good mechanical integrity. If we have a ratata ratata ratata, then we know we got one cylinder or more that might be low on compression. And of course, I got to give a shout out to my boy Paul Danner. I jacked these videos from Paul, so if you guys, my bad. Okay. Also, I forgot to put this on here. If you guys want to kind of take a note of this, if you have a car that's a crank no start, one of the quick things you could do is put a vacuum gauge on it and crank it. Right? If the engine integrity is good, we should have between 2 to 5 inches of vacuum while cranking. If I have no vacuum while I'm cranking, then I have bad engine integrity, which usually is a bad valve, a bad timing chain or timing belt that might have gone, and that's what's causing the engine not to create any vacuum. It's not going to be a steady needle. It's usually going to be bouncing, and that's because the engine's only cranking at about 200 RPM, right? So we have to keep that in mind, but at the same time, that's a good indicator. I remember in the early 2000s when Kia was really bad, a little bit worse than what they are now with timing belts, right? You see a Kia roll up on the tow truck, then you kind of knew it was like, all right, cool, this thing probably timing belt went out, right? So you'd ask a tow truck driver, what's wrong with the car? Oh, it cranks, but it doesn't start. All right, go get a vacuum gauge, put it on there, and crank it. If you got no vacuum, engine's shot. At that point, it's like, you sure you want to pay me for a diag, or you just want to get an engine, right? Because those are interference engines. That timing belt went out, piston hit the valves, and it was gone, right? So it was a big thing back in the day. When it comes to compression, one thing I always see is I see a lot of techs only run a static compression test, which is good, right? We're checking the engine's ability to breathe properly and build compression. Now, when we do a compression test, typically we want to see all cylinders be within about 10% of one another. So we're looking at these here. How do these look? We got 160, 155, 130, 160. Would you guys consider any one of these out of spec? 3? I'd say so. Yeah, we got cylinder number 3 at 130. It's relatively lower compared to everybody else. If it was somewhere about 155, 150, wouldn't really bother with it, but we're at $130. So that cylinder's a little bit low, right? So from there, the next test I would want to run as a tech would be a running compression test on cylinder number 3, right? Because cylinder number 3 has already showed on a static test that it's low on compression. So I'm going to follow that up with a running test. And a running test, typically, this measurement should be cut in half, right? Yep, number 3. So now, with a running compression test, the engine should be 50% or half. So if we look at these examples here, and I'm at 130, and then what's my running compression? 35. So double 35 would be 70, right? We got a big problem there. Because if I look at cylinder number 1, it's 160, and we're at 80. 2 is 155, we're at 78. And number 4 is 160, we're at 80. So number 3 has a big problem. Now let's analyze these numbers to kind of get a better idea what's going on here. If cylinder number 3 running only has 35 PSI, what's happening here? Is that like restricted exhaust, or is it possibly that engine can't breathe properly through the intake valve? Or could it also be we got a valve that's not sealing properly, and every time it's compressing, it does this, right? It pushes that pressure out through a valve seat that's not 100% there, right? They said that shit's broke. 100%. So on cylinder number 3, $130, $135. At this point, my next step I would do as a tech is a cylinder leak down test, right? Because now I want to find out, where's this volume going? Is it not taking enough air in, or do I got a leak somewhere, right? And what I normally end up seeing is I'll see a tech run a compression test, but all they do is a static test. And, oh, they all look good. Did you run the engine? No. Why not? Right? Obviously, if the engine's not under stress, it's going to be able to do some work. But the moment that we stress that engine, we might not be able to build enough compression. Or what if it's leaking, right? So we need to make sure that we do that static compression check. Now, from there, we would do the snap test. Whenever we do a snap compression test, we should get about 75 to 80% of your cranking compression. So if we look at these numbers here, cylinder number 3, cranking compression was $130, and we do cylinder 3 a snap test, we got 123. So it came up pretty good, right? But if we look at cylinder number 2, we're at 155, and what do we measure here? 77. So we got a problem there, right? Okay, so if the snap reading is higher than expected, there's an issue with the exhaust side of that particular cylinder. If the snap test reading is lower than expected, then that's an issue with the cylinder inhaling. So you might have an intake issue, right? So this is a good way for us to verify that. Now, I know some of you guys might be using oscilloscopes with in-cylinder pressure transducers, delta pressure sensors, or absolute sensors, but they're not going to be asking you that on the ASE. We're still old school on the ASE, using analog gauges and all that fun stuff. So we need to understand how to be able to look at these numbers. If we're able to put all these numbers together, then that's going to give you an idea of where that problem might be, right? So now that we've done this actual testing, the next thing I need to do, like I said earlier, is a pinpoint test. I need to pinpoint it. How do I pinpoint it? Leak down, right? If I do a leak down test and I see or I hear air gushing out of that exhaust, right? I could put a glove over the exhaust. If it fills up, got an exhaust valve that's bad, right? Or if I take the oil cap off and all I hear is air coming through, then I know I got some rings that are shot. Okay. I had a student in my last class about a week ago, brought in a BMW, and the BMW had a link code 171. And what was crazy is when we started testing it, we tried to pull the oil cap off and it wouldn't release it. So there was vacuum inside the crankcase, right? What we did is we wanted to test the theory, so we got our propane rig, and we opened up the fill cap and we hit it with propane, and we were watching our short-term fuel trim. And when we did that, our fuel trim changed. It went lean. It started taking away fuel, so that's how we figured out, cool, vacuum's interconnected with crankcase. We just confirmed that we have a PCV valve. That's bad, right? So we recommended replacing the whole valve cover to change the diaphragm. Okay, there's better ways of doing it, but that way worked. Okay, a manometer is another way you can do it by comparing internal pressure to atmospheric pressure. I have one, but I'll be honest with you guys, I haven't tested it yet, so I don't know how to use it. I still go with the old school methods like propane. Works great. Don't be squirting carburetor cleaner inside the crankcase. Make sure you use propane. Here, what we're looking at is doing an old school cylinder leak down test. You want to raise the cylinder top dead center compression. That's going to close both valves. And then we're going to apply shop air. Typically about 0 to 10% is considered good. 10 to 20 is fair. 20 to 30 is poor. And 30 to 100 is failed, right? We have piston rings and they all have end gaps. When we assemble an engine, end gaps don't align, so they should be protecting some of that compression. If we do a cylinder leak down test, and we have air coming through the air intake box, then we know we got an intake valve that's not seating properly. If we hear it through the exhaust and the exhaust valve, if we hear in the PCV, then we got rings, right? And then if we see bubbles in the coolant, then we know it's a blown head gasket or cracked block. Recently, I was introduced to a new method of doing this, and so far, so good. What we do now is we raise it top dead center compression, then we bring it down to bottom dead center. At bottom dead center, we're also testing not only the valves for sealing and also the head gasket, but also the integrity of the cylinder. So if you bring the piston down to bottom dead center and you run this test, right, and you're getting a shitload of air in the cooling system, it's probably going to be the block, okay, not just the head. So this is another step in a better way of testing, right? What I always recommend is you want to try something like that, try it on a car that's good. So one of your cars or a car that you know doesn't have a problem, test it. Okay, that's how you want to test theories. Don't test them on broken cars. When it comes down to the leak down test, if it's over 20%, then obviously we want to see where it's coming from. And this is where gloves come into play, We'll put a glove over the oil fill cap and all that fun stuff to kind of see if we have a problem there, right? If I feel that it's a problem with the rings, I'll use a delta pressure sensor with my oscilloscope, and I'll remove the dipstick whenever possible. I'll put it on the dipstick, we'll disable ignition, and we'll crank it. And as the car cranks, if I keep seeing a repeating spike in pressure, then I know that we have excessive compression or blow-by going into the crankcase. Now, if I want to know which cylinder it is, then I'll synchronize off a coil. And then if I get a giant spike on cylinder number one, then I know cylinder number one is the one with the bad rings. So we just basically did the diag with that one test. Yeah, so that's another way that we can do it. I don't think they're going to be testing you guys on ASE, but that's a good way we can do it at the shop, right? And if we have any air bubbles in the cooling system, that usually indicates we got a blown head gasket or a cracked block, right? So then we got to figure out where it's at and then go from there. All our shit's broken, has lights on for days. Sounds like a Kia. It's like a Christmas tree, right? Those are actually European cars you get on offer of, right? They show up with every imaginable light on. It's like, dude, I got it cheap. Yeah, there's a reason why you got it cheap. One of the things they're going to test you guys on is 5-gas analysis. Okay? I always get this from everybody that's outside of California. They're like, dude, I don't use a 5-gas. Yeah, they hate it. It's like, man, you know how much I love my 5-gas? 5-gas thing is freaking awesome. Okay, we're still required here in California to have 5-gas analyzers, so we still have it, and the thing works bitching. Okay, when you have your 5-gas analyzer, you can throw it in the tailpipe. You can kind of get an idea of what's going on with the car simply by looking at the 5-gas reading coming out of the tailpipe. I've had some shops out in different states that don't have 5-gas analysis. They're like, dude, should I buy one? So if you really see a need for it, get it. But I will not. That's not something that I'm going to tell you guys. Like, if you don't have one, you need a 5-gas. No. But if you do pick one up, you're going to love it. These things are freaking awesome. What we're looking at here is your engine's going to inhale nitrogen and oxygen. That's going to be all the air coming in. And then our fuel is made up of hydrogen and carbon, which is HCs. We put those two together and compress them, and then we ignite them. Once we ignite them, we're going to create these gases coming out the tailpipe. First one's going to be water, H2O. That's why we get small droplets of water coming out of the exhaust. The old rule of thumb is for every 1 gallon of fuel we burn, we're going to have 1 gallon of water coming out. It's a 1-to-1 ratio. I don't think you want to sit there and kind of measure to see how much fuel you're burning and then how much water is coming out of the car, but that's just putting that out there, right? If we have some sort of incomplete combustion, ignition, mechanical, or some reason cause the engine not to burn the air-fuel mixture properly, we're going to have some hydrocarbons left over. So HC is unburned fuel. When we have oxygen and carbon combined, we're going to form carbon dioxide. When I don't have enough oxygen to form carbon dioxide, I'm going to form carbon monoxide, the silent killer, right? The one that kills you. So carbon monoxide is actually a byproduct of internal combustion, and that's created when I don't have enough oxygen to form CO2. This is why we always say that when a car is running rich, we have too much fuel, not enough oxygen, right? Because we can't create CO2, so we start creating carbon monoxide, one oxygen molecule. Then we're going to have some oxygen left over. With most newer cars, we have very little oxygen left over. Then we're going to have nitrogen combined with oxygen to form NOx. So the reason why there's an X here, that could be 1, 2, or 3 oxygen molecules combined to nitrogen. One of the downsides about nitrogen is nitrogen has a property of expanding with temperature or pressure. So it starts using up volume within the combustion chamber. And we need to remember that because that comes into play when we start analyzing 5-gas readings out of tailpipes. Okay, so CO2 is typically measured in percentage, and we use this as an engine efficiency indicator. Typically, you want to see about 13 to 15% CO2, and if we have low CO2, that usually indicates a mechanical fault. Okay, and by low, I don't mean 13 or 12, I mean 9, 9.5. Okay, that's going to be indicating a mechanical problem, right? The next one would be O2 or oxygen. This is usually an efficiency indicator as well, but more for the cat. I use this one in combination with CO2 to then determine engine efficiency. If I have low CO2, let's say 9, and about 3 to 4 O2, then I have a big problem, right? I have too much oxygen left after internal combustion. What does that mean? I didn't burn it. If I have 4% left after it's supposedly burned, it didn't burn, right? And if CO2 is that low, then we didn't ignite it, we didn't compress it, and we didn't convert it. So it came out pretty much raw out of the tailpipe. Okay, so that's indicating to me I had a misfire of some sort. Does that make sense? Yeah. And if we go to the next one, hydrocarbons. Hydrocarbons is measured in parts per million. The fuel that goes into an engine is hydrocarbons, right? HCs. If I don't burn it properly because it's not compressed, it's going to go right out the tailpipe. Okay. So if you notice here, if I have high hydrocarbons with high oxygen between 1 to 2% and about 12 to 13% CO2, that's an ignition misfire. Okay. And that's a quick and easy way for me to kind of get an idea if that's what's going on. And hydrocarbons for an ignition misfire is only going to be about $1.50, $1.60. It's not going to be that high, right? But then if I have a mechanical misfire, I'm going to see somewhere about 300 to 400 hydrocarbons, roughly about 2 to 3% O2, and about 9 to 10% CO2. And that's how we're going to know, okay, that we have a mechanical misfire. And they're asking the video. Yes, the video is going to be online, so you guys will also have access to it, so you guys want to watch it. Okay. You're going to get questions on the ASE exam where they're going to give you 5 gas analysis, and you got to analyze it and see what's wrong with the car. Okay. So being able to put all these pieces together, we can have an idea of what's going on with the car. When I run this class here in person, we'll create mechanical faults with the car. Typically what we'll do is we'll screw a spark plug out where it's almost popping out of the hole. And then we'll create that mechanical loss of compression and we'll run it. And then that's when you'll see 400 or 500 hydrocarbons, about 9% CO2 and like 2 to 3, sometimes 4% O2. You put all those pieces together and it's like, okay, cool, I got a mechanical fault here, right? So then now you can direct yourself into where that problem might be. Also, I show my students this. I'm pretty sure you remember this, Rico, but back in the old carburetor days, a car came in with a crank no start, we'd put the probe in the tailpipe. Or if it was a throttle body injection, same thing. And we'd crank it. If I had no hydrocarbons reading, I didn't have fuel. So that means I have a fuel control problem, right? So that was one of the quick and easy ways we used to do it back in the day as well. It just depends how we felt and if the bay where the smog machine was empty, right? Pull the car up, just put the probe in the tailpipe, crank it. If you have no hydrocarbons coming out the tailpipe, you have no fuel, right? Because the car is not starting, it's cranking. So if I put the probe in the tailpipe and I'm cranking and I got 100 plus hydrocarbons coming out, I have fuel to begin with. It's just not being ignited, right? So at that point, then I know, okay, cool, it's not fuel related. This is probably going to be ignition. Okay, so this is another way that we can use a 5 gas analyzer to kind of figure out where you're headed with your diag, right? CO, carbon monoxide. Carbon monoxide is also measured in percentage, and this is created when there's not enough oxygen to create CO2. Typically, this should be about 0, and when CO is low, that means it's lean, and when it's high, that means it's rich. We don't have that many problems now like we used to back in the day with rich conditions. I remember cars used to come in sometimes 5%, 6%, 9%, right? These things look like diesels, just black smoke coming out the tailpipe. And that was because they were running extremely rich. We don't have that many problems anymore. The most common problem we see now are lean conditions, 171s, 174s, right? So that's all coming with the cars that we're actually working on. Snap-on 5 gas analyzer added to cart. Ouch. Hey, you get some free socks with that, right? Maybe some beef jerky. Or a pocket screwdriver, right? They always get you with the pocket screwdriver. Yeah. It's like, here, you want the toolbox, you get a hat. Oh, shit, man, sold. All right. The next emission we check for is NOx, oxides of nitrogen. This is measured in parts per million. And this usually is created when nitrogen heats up and expands and it combines with oxygen. This one should roughly be about 250 parts per million. And temperature above 2,500 degrees Fahrenheit, that's a key number there. That's going to create the pressure effect and create NOx to actually go up. One of the things you want to remember when it comes to NOx is if you're looking at any test, I don't care if it's an ASE exam, an emissions exam, if it's referring to NOx, the first thing come to your mind is an EGR valve. If this vehicle has an EGR valve, the EGR valve's responsibility is to help us reduce NOx by pushing spent gases back into the combustion chamber. They're already burnt, so we can't reburn them. That's going to cool down the combustion chamber. And when that happens, we're going to have a lower NOx level. Okay, so we always want to make sure we remember NOx, associate that with temperature or pressure, right? If I have a car, okay, we used to see this quite a bit when every car was dyno tested. If I have a car that runs 91 octane, right? So that means it's a high compression engine. If I run low octane fuel, that fuel is going to begin to burn before the engine actually compressed it all. So then that causes pinging, detonation, which causes NOx to go up. So we used to have these cars come in a bunch, especially the Europeans, and we let them know, go run some high octane fuel and then bring it back. And then they'd give you that face like, I'm running on high octane. Yeah, right. And then when they'd come back, the car usually would pass. And that was because we knew they were not running the proper fuel. Okay. Also, timing was a big deal. A lot of the old timers used to mess with their timing to try to get more performance out of the car, but then that would affect NOx. We'd run it on the dyno and they gross pollute for NOx. At that point, we would go and check timing. Timing was through the roof because they were trying to get some power out of it, right? Then we would just readjust timing and then car would pass for NOx. Carbon buildup can also affect NOx. So NOx is that one emission that could be super easy to fix or pain in the ass. There's no in between. It's easy or it's a fucking pain in the ass. Okay, so whenever you guys are dealing with a NOx issue, just make sure that you guys are aware NOx is temperature or pressure. Anything that affects temperature or pressure within the combustion chamber is going to affect NOx. Okay. So here I have a couple of emission gas readings that we could take a look at. So this first car here has 15.6% CO2, 0% O2, 68 hydrocarbons, CO is at 0.11, and then NOx is at 144. What I did is I put this on the Lambda calculator. I love using a Lambda calculator because this gives you stoichiometric, right? Stoichiometric is 14.7 parts of air to 1 part of fuel. If I have good fuel control, that means my catalytic converter is going to do its job, right? This is why I always use 5-gas and Lambda. A lot of people use it for cat efficiency. I use it for engine efficiency. If my engine's running efficient, obviously my cat's going to have 100% efficiency. But if it's running efficient, then I know I have fuel control. The computer's in control of making those adjustments, right? So that's why we run these calculations. So if we look at it here, my Lambda reading is 0.995. Lambda ranges from 0.980 to 1.020. That's the operating range that's good fuel control. 1.0 is perfect stoichiometric, right? For me as a tech, I want to be at 1.0. But if I'm not at 1.0, it's not the end of the world. 0.995. I'll take that. Okay, we have fuel control. This is probably an older car. If this was a newer car, that shit would be at 1.0. Okay, if you guys are working on some newer cars that have a air fuel ratio sensor in the front or a wide range or wideband O2, you see it in Lambda on your scan tool. Okay, so being able to understand what Lambda is referring to, you see that on the scan tool and it says Lambda's 1.0, we know for sure we got fuel control. Okay, so we should be good coming out the tailpipe. The vehicle should be running normally, and there shouldn't be any customer complaint or concern about high fuel consumption, right? Because the PCM is doing what it needs to do to make sure that fuel is 100% on point, right? If you guys run into a scan tool that you're looking at and you notice your Lambda is at 0.8, that thing's running stupid rich. You got a rich condition. Okay, if you see that Lambda's like at 1.1, 1.2, it's running stupid lean. Okay, so those are a couple of numbers that we want to pay attention to. Even without a 5-gas, just remembering that with Lambda, we know for sure that we don't have fuel control. So here's another one. Okay, and check out what it says at the bottom. Vehicle has a mil on with P0300 DTC. And then I'm asking, is it really lean? So if we look at our gases, 5-gas coming out the tailpipe is 10% CO2, 3.5% O2, 320 hydrocarbons, 0.11 fuel, and 42 NOx. If we punch that into a Lambda calculator, my calculator says 1.205. That means it's excessively rich. Excuse me, lean. Anything above 1.020 Lambda, you're already going into that lean misfire zone, right? And by looking at these numbers, and then also paying attention to a P0300, 10% CO2, 3% O2, right? 320 hydrocarbons. I don't have a lean condition. What kind of problem do I got? This would be a mechanical problem. So with this one here, we can see that I'm going to be chasing mechanical. I'm not going to check ignition. I'm not going to check spark plugs. What does this thing really need? Probably a new engine. Okay. So looking at this is how we're able to determine how we're going to proceed with our particular diag, right? Just by looking at these values here. So the question was, is Lambda different between manufacturers? Because in a Toyota Diag class, it was told that 1.20 Lambda meant rich. No, it's from what I know, Lambda is going to be this operating range. So anything 1.0 and higher is lean. Anything below that is rich. Okay. So if you guys run into a vehicle that you look at Lambda and it's showing 1.1, go look at your fuel trim and it's going to be plus positive because it's running lean. Okay. Matter of fact, we actually checked the BMW with one of our students, another BMW with one of our other students, and his car had a lean condition code. And what we did is simply here in the shop, we were looking at scan tool data and we just gunned it, right? Because if we go wide open throttle, in wide open throttle, that's a enrichment mode. So the PCM goes into open loop, right? If you guys have looked at live data, when you go into wide open throttle, PCM goes open loop. So it's not looking at sensor data. When we did that for a reason, because at that point, if the problem was sensor input related, right? We would have seen front sensor go full rich, which would have been below 1, and then rear O2 go full rich would have been high, right? Close to 900 millivolts. When we did that wide open throttle acceleration, what we saw is his front air fuel ratio went up to like 1-2, and then the rear O2 dropped to 0 during that wide open throttle. The PCM did go into open loop, but there was not enough fuel volume to actually sustain that rich condition. So that's how we were able to determine that it was a fuel delivery problem. He worked at a shop, so then he took it with him and he ran some tests and found out it was a bad fuel pump, low volume, so they replaced the pump. So that's an easier way too that we kind of run with to kind of figure out if we got fuel control, right? Because remember, if we go into open loop, PCM's like, done. What if I'll give you everything you got, right? So if I whack that throttle and I don't see a rich condition, then that means I don't have enough fuel to feed that engine, right? That's a good way to go about it. Okay. Any questions up to this point? Go for it.
Where did you say you could find that calculator?
The Lambda calculator. So if you guys, I have one that I created. It's, you go to stopthestarprogram.com, and on there I have a Lambda calculator, I have a VE calculator, a fuel volume calculator, and a engine load calculator is what we have on there so far. So it's stopthestarprogram.com. In a couple of slides, when we talk about fuel, I'm going to give you guys a link, so that way you guys could go directly to it. All right, so let's talk about ignition. Obviously, when you're taking the ASE test, you can't just sell them coils and plugs, right? We actually have to check it. So we're going to talk a little bit about ignition, diag, and some repair. And this is going to help you guys when it comes time to take your A8. I took the T1 recently, which was heavy duty gasoline engines, and they had a shitload of scope captures. So I'm not sure if the A1 has that, but the T1 had a bunch. So if you guys are planning to take the medium heavy duty gas engine ASE, there's a crap load of scope captures on that one. Okay. Anytime we have a vehicle with a misfire or a drivability concern in general, it can only be one of three things. a mechanical problem, an ignition problem, or a fuel problem. That's it. If we're able to remember that it could be one of these three things, it's going to help us really get quicker at a diag, right? What ends up happening is most shops and most techs think that a car is only going to misfire for ignition. That's why they always throw plugs and coils at it. And when that doesn't fix it, then they don't know what else to do. Well, if we remember that the engine has to mechanically take in air and fuel and compress it, then the ignition system takes over, right, and ignites it. If I have a problem with any one of these two, I'm going to have a misfire. If my fuel, low volume, bad injector, right, that's also going to affect the way the engine burns the air-fuel mixture. So we need to make sure we remember it can only be one of three things: mechanical, fuel, or ignition, right? And let's see, we got some questions. What does it mean when you see a negative 25% short-term and positive long-term on a four-cylinder engine? Nothing wrong with it. Total trim is 0. So if we see positive and negative, they're going to kind of zero out sooner or later. So the question was, if I see negative 25, positive 25 on one as total fuel trim, they're going to zero out, right? However, you got one that's adding 25% fuel and the other one's taking it away. So this means you got a fuel imbalance. Typically, that could be a sensor input, or it could be a mass airflow, a load sensor, something of that sort that could be causing that type of condition. When it comes to going back to these three here, I always think of fuel in this way. If I get a car that comes in and it doesn't start, or it has a misfire, right? And we do this when we're playing with a 5-gas analyzer. If it's an injector problem, how is your exhaust going to smell? Let's say your injector is not firing, right? And that's causing your misfire. How's your exhaust going to smell? Like rotten egg or normal? What do you guys think? So if I go out to a car and my injector is firing, I'm going to get that rotten egg smell. You guys remember stink bombs? Yeah, it's going to smell like that. Now, if I have that smell at the tailpipe, my injector's firing. If I go to the back and I don't have that rotten egg smell, then I know for sure it's not firing fuel. So the problem I have with that misfire is fuel related. So now I need to go look at that injector to make sure that the PCM is turning it on and off, right? If I go do that, I go to the back, smell it, and I don't have I have the rotten egg smell. It's not fuel, so it's going to be now one of these two. Does that make sense? Okay, so then now we can focus on mechanical or ignition at that point. Engine mechanical could be determined quickly by a general test like a relative compression. The dollar bill test. Okay, this is old school technology. What you do is you take yourself a piece of paper, you put it on the exhaust pipe. If all cylinders are firing properly, I should have positive pressure coming out of it. If I see that dollar bill or that piece of paper get sucked in every so often, then that means we got a valve problem. Okay, for sure at that point, it's mechanical. Okay, I could use a vacuum gauge, or I could listen for cadence. Use your ear, right? After mechanical general tests, if they all seem normal, then move to the next one. Go to ignition. So I can use my oscilloscope, connect it across the battery, positive and negative, change it to AC volts, about 20 volts, then crank it, right? If I get a waveform and all the humps are normal, then I got good relative compression, right? I can also run that test from the DLC, going pin 4 and 16 of the DLC, or go grab $20 from your boss and see if it sucks it in. If it does, cool, then you know for sure, and then roll up the 20 and keep it. It's a tip. Yeah, right? Like, what, $20? You didn't give me $20. I got lunch, right? And then a vacuum test, you put a vacuum gauge on it, and if I got a bouncing needle, right, about 2 inches, then I know it's valve train related. Okay, so running these tests are going to quickly help us identify what's going on with the car. Back in the day, this is what we used to see on the primary side of ignition system. When our points closed and we would see voltage drop down, so that was this right here is our dwell section. This is when the points would close and we would have current flowing to the coil. Coil was being saturated on the primary side, on the low voltage side. Once our points opened up, then we would have this giant spike of voltage. This is when it was dropping or being absorbed from the primary or primary side to the secondary side. Also, that same voltage line there represents the amount of energy required to begin to jump the spark plug gap. Okay, so that's why You can see that there. On newer cars, we have what looks like this. On newer ignition systems that have coil on plug, particularly coils that have more than 3 wires or 3 wires or more, the only way you can test the primary circuit is by using an amp probe and an oscilloscope. Like we were talking about yesterday, if my resistance within the coil is normal, I'm going to see a gradual saturation of current, which is this blue ramping line coming up. If I have a coil that's shorted with very little resistance, we're going to see a direct vertical rise of current. Okay. So notice that we could see this just ramp up nice and smooth. Then we have a plateau right here at the top. This would be what we call current limiting. The manufacturer has limited the amount of current at this point to this point because it doesn't need any more. That probably means that this capture was done at idle. If this vehicle was at high speed, we'd probably see this come straight up to a peak and then back down. Because it has that plateau right here, that's telling me this car was probably at idle and we didn't need all that extra energy, right? So that's how we're able to see that using this. If you have the availability on a 2-wire coil, you can always back probe the ground control to the coil to get this particular waveform on the primary side. The reason why, if you want to start with primary, if you have a problem on the primary, you're not going to have a good secondary. Okay, so that's always important to understand. Primary comes in first. If your primary is fucked up, there's no way you're going to have a good secondary. There's just no way. Okay. If you guys are going to be connecting directly to the coil with your scope, make sure your scope can take it. On a pico scope, you want to use an attenuator because a pico scope only has 250 volts per channel. And if that coil for some reason draws or pushes more than 250 volts, you're going to fry your scope. So what the attenuator does is the ones that come with pico are 10 to 1. So for every 10 volts in, you get 1 volt on your screen. Okay. I also have 20 to 1 attenuators. So for every 20 volts in, I get 1 volt on the actual screen. Okay. Right. And some European vehicles will have 3, 4, 5. I've seen 5-wire coils. So be careful with that. Make sure you guys pay attention. How does that coil operate? Okay. Looking at our old school ignition system, last time I took this test, they were still asking some of these. So this is the reason why I put this on here. Back in the old day, when we had distributors, rotors, caps, okay, bless you, we used to set up our scope and we would do a superimposed pattern. Superimposed means that all cylinders are overlapped one another. And this is going to help us relatively quickly be able to see an entire overview of the whole ignition event. And if I had an ignition or a cylinder that was not normal compared to everybody else, it would stand out, right? Obviously, I'm not going to be able to say, oh, it's cylinder 3, but I'm going to see that 1 or more cylinders is acting up because that waveform is going to be a lot different than the rest of them. That's why we would use a superimposed pattern. When we were doing these, the way we would connect this would be one connection went to the coil output and the other one went to cylinder number 1. So the big box scopes, that's how we used to use them. And we would also use that on the MT2400 or any ignition system that you would be using. It would always be one to the coil and one to cylinder number 1. And then you would enter your firing order and your scope knew how to set it up based off of that firing order. So it was pretty cool the way that that system actually worked back in the day. When you're looking at the ignition firing event, we split it up into 3 sections. We have the firing section, the intermediate section, and the dwell section. Okay. So during the firing section, this is when we're going to have this giant spike of voltage, which is the voltage required to overcome any gaps if you have a distributor or any resistance in the ignition system before it begins to jump across. So here, this is the amount of time the spark plug is actually firing inside the cylinder. Towards the end, as it runs out of fuel, this is why we get this upward rise in voltage here, because it ran out of fuel. That would be the firing section. Right after the firing section, back in the day, you wanted to see at least 3 coil oscillations, meant that that was the residual energy dying down. And then at that point, you would see it just flatline all the way across. That would be the intermediate section. At the end of the intermediate section, we would start the dwell section. This is when your points used to close and then voltage would get pulled to ground because now you're saturating the coil again before the coil actually fires. So that would be the 3 sections that you would be using when you're looking at an ignition system. This still applies today. Okay, just because we don't use distributors, cap, and rotors doesn't mean that this doesn't apply. We can still apply this today on an ignition coil. When we're looking at our actual waveform here, on part A, as you guys can see here, voltage gets pulled down. So when that gets pulled down, that's going to be our dwell section, the start of the dwell, right? We're pulling the coil to ground, so we're beginning to saturate the primary side of the ignition coil. On part B, or point B, notice how we had that voltage ramp, and then we had that little flat line, that plateau. So it plateaued there because we're current limiting. I know this because I took this capture. The car was at idle. Okay, so the computer's not going to let you create too much energy because you don't need it. It's at idle, right? When do we need all that extra energy? High speeds. If I would have taken this capture at 75 miles an hour, wide open throttle, hell yeah, that shit would have been all the way across because I need all that energy, right? But if I'm here in the shop chilling, we don't need it. So that's why we have that plateau. That's current limiting. At point C, that's when we turn off the primary side of the ignition, and then boom, this is all the voltage required on part D, okay, to begin the ionization of the spark plug gap. Okay, so from there, from point C to point D, all the way to the top, that's voltage going up and beginning to ionize the small gap of your actual spark plug. Okay, so this will change depending on changes inside the combustion chamber, right? If I do a snap throttle, that's going to increase pressure inside the engine, right? So that's going to make it a little bit harder to fire. So that line right there at D needs to get longer if I'm at high speed or wide open throttle. Why? Because it's harder for it to burn, okay? Then from there, we go to part E. Part E right here is the voltage that stabilizes from roughly 200 volts anywhere up to a few thousand. Okay, this is where plasma is created and spark begins to travel across the actual spark plug electrode. So notice how here, from this bottom point there to where E begins, it's not that much, right? If I were to see E starting somewhere up here, what is that indicating to me? If it's beginning the burn process at a higher point than what's normal, what do you guys think that would mean? Would you guys agree that if I start at a higher point, that means we have a lot of external resistance? Okay, so that would be your answer. If you see this burn start way higher, that means you have a lot of external resistance. That could be bad spark plug wire. That could be a burnt rotor. That could be a burnt cap. That could be coil boot, right? Anything that's outside of the combustion chamber. So we look at F, right? F is right here pointing towards the center. What you want to remember is at point F, anything to the left, right? So I'm going to go over here. Anything to the left of this burn, so anything on this side is external to the combustion chamber. Anything to the right side of the halfway of the burn mark is internal to the combustion chamber. Okay, so this is how we need to remember this for secondary ignition analysis. Also, at point E, if at point E you start seeing your voltage go up, a voltage rise during ignition event indicates lack of fuel. And voltage drop during an ignition event means it finds fuel. Okay, so if I'm looking at an ignition event that's going up, down, up, down, up, down, and that car is at idle, that's telling you that it's not finding fuel, it found fuel, not finding fuel, it found fuel. So that's an indication that for some reason we have like a swirl effect or something going inside that engine cylinder that's causing the air to molecules to be moving around, right? So that could be turbulence that we call it. So that could be a valve that's not sealing properly, carbon buildup, right? All of that could be affecting the way that we're actually burning that air fuel mixture. So typically we want to see it come across relatively smooth, not too smooth where it looks picture perfect, because then at that point, you know it's not being affected by any type of event within that actual cylinder, okay? So we continue here. This is the important part. What you want to measure anytime you're analyzing ignition is you want to measure from, let me get this damn thing to point here. There you go. So when it starts off from here to here, That's your burn time. Your burn time needs to be 1.0 to 1.5 milliseconds. That's it. If it gets shorter than 1.0, okay, if your burn time gets lower than 1.0, that typically means you either have a wide gap or low on compression. Okay? Excuse me. Wide gap, just wide gap, not the compression part. If for some reason it's wider than 1.0 to 1.5, okay, then that's going to tell you that you have a closed gap or you have low compression. Okay? Now, again, like I was saying, you want to split the burn time in half. So at point F, you want to cut this in half. Anything to the left of it indicates a problem external of the combustion chamber. Anything to the right of it indicates a problem internal of the combustion chamber. So let's look at it this way. If, let's call it at the halfway mark, at that F point, you begin to see that your burn, instead of going across, starts becoming super jagged, right? Major jagged, but the car is at idle. Where's the problem? Is it internal or external? If it's on the halfway mark to the right, internal or external? Internal, right? So what would be the only thing that could be affecting or causing such a turbulent burn once it goes inside the engine? Could it be a valve? Yeah, right? So typically that would be a valve problem or carbon buildup, okay? And you're seeing that simply by just analyzing this part right here. Now, if you would see that from the get-go, okay, where your burn starts at point E, you see it automatically begin to rise up. The moment that it starts firing, that thing just shoots up. Okay, what does that mean to you if you start seeing it from point E, right at that particular point, you see that thing just shoot up this way. What is that telling you? So that means it's excessively lean. And if I see it start right at point E and start shooting up, that's an indication to me that this vehicle didn't have enough fuel to begin with. So more than likely, it's probably going to be an injector problem, right? One thing you guys always want to keep in mind anytime you're analyzing ignition waveforms, don't do it just at idle. You want to raise the RPM. Preferably, power brake it, because we're stressing the engine at that point. So power braking it, we're going to be able to make that engine suffer a little bit so we can get a good analysis of that actual waveform, okay? From there, a couple other things. A nose. If you have no nose, that means spark didn't enter the combustion chamber. So at the end, you guys notice how here, right there, this looks like a nose, right? It gives you that ramp effect and then it comes back down. We call that a nose. So if you have that, that right there is indicating that the actual voltage or spark entered the combustion chamber. If you don't, where it just goes straight across and then drops, it didn't enter the combustion chamber. The other thing is you want to make sure that you have those small coil oscillations right there at the end where you get those squiggly. That's residual energy that wasn't able enough to continue the spark, but then it's going to bleed off, okay? So power braking, question was, what's power braking? Power braking is when you put it in drive, apply the brake, chalk the wheels, and then give it some gas where it's about to burn out, but don't burn out, right? That you're kind of forcing the engine at that point, and that's a good way for us to test or stress test the ignition system, okay? All right. So looking at this one here, this is an old school technique which still applies to this day. If you guys look at this waveform, right, notice how this is like dots, right, or dashes. So the firing line should jump abruptly the moment throttle is opened and return to the previous level. So if I have a car sitting in my bay and I whack the throttle, I should expect that voltage, that vertical line, the kV, get larger, right? And then as I let go of the throttle, it's going to come back to normal. Why did that happen? Well, when I went wide open throttle, I had that inrush of air coming in, and that created a harder, what would you call it? A harder environment for the spark plug to actually fire. Because of that, that's why we had that instantaneous increase in voltage. If you have no change in firing kV, that means you have a valve issue. Okay, that's simple. If I have my paddle probe or my scope on the car and I whack the throttle and I don't see it jump, it stays the same, what happened? We didn't have inrush of air. Okay, we didn't have a valve problem at that point. So now we can confirm we got a problem, right? It was easier back in the day because we were able to do a parade pattern like here and see all our cylinders side by side. But now we don't have those capabilities with our scopes. So usually what I do is I'll set my scope to about 5 seconds per division. I'll do one cylinder at idle, snap it, high speed, low speed. Then I'll leave a time gap. Then I'll go to the next one, do the same thing, time gap, so on and so forth. So then I can go back and reanalyze it. If you don't have a G, you don't have an H. All right. The next one, you want to raise the RPM up to 2,500 RPM and then quickly release the throttle. If one cylinder drops later than the others, this indicates that you have a weak valve spring. Okay? That's gold right there. So if I were to go ahead and raise the RPM at 2,500, I'm holding the throttle open. The moment I let go of the throttle, right, what should happen? Read that bottom one. The moment I let go of the throttle, we should have a drop. If we have one valve that takes longer to come down, what does that mean? Valve spring problem. Okay. Now we can follow that up using a vacuum gauge, and then that's how we're going to be able to see if we have any other issues. Yeah. So they're saying that it kind of sucks on V6 when you have an intake manifold in the way, and like Lexus V6s. That is true. What's another way that we can check ignition though? I could pull a fuse, put a wired jumper fuse, put an amp probe on it, and then at that point we could see primary side, right? The paddle probe is also pretty cool because on the paddle probe, I've bent the shit out of mine and I'll shove it underneath manifolds and I can get waveforms out of it. So we just kind of have to look for a good way to actually pick it up. If you're getting a firing KV that keeps getting larger or shorter, let's think about that. I told you guys KV, right, is how much resistance we're creating within that cylinder. Do spark plug boots or coil boots get longer or shorter? No, they should be relatively the same. So if you have one cylinder that keeps getting larger, smaller, larger, smaller, larger, smaller, what kind of problem could that be? What do you guys think? Probably a carbon valve or burnt valve. Okay. So by looking at that, we can see like, all right, cool. If I'm watching a cylinder and I just see that thing go large, small, super fucking large, very small. Okay. And it keeps doing that, then I got a burnt valve or might have carbon buildup on the valves, right? Pull your borescope out at that point, kind of figure out, is it a fouled valve, a burnt valve, or is this the carbon fouled, right? Okay. Any questions on secondary before we move on? Okay, so we got a question that says paddle probe checks primary side of the ignition. So the paddle probe is going to check secondary. What the paddle probe is it's a inductive pickup, sits on top of the coil, on the side of the coil. Sometimes some cars are heavily insulated on the coil. We've had to put some on the side, on the top, it just depends. But you lay it on top of the coil, and then that picks up the magnetic field of the coil, and that's how we get a waveform on the actual scope. So using the paddle probe works out really, really well. There's a lot of different variations of them, so you just got to make sure you shop around, try to get a good one. Okay, so we're going to talk real quick about load sensing within an engine. So typically, engines have two ways of sensing load. When we talk about load, we're talking about how much work the engine needs to put out based off of your driver command, right? So we have two different systems. We'll either have a speed density system or we'll have a mass airflow. If the vehicle you're dealing with has a speed density system, it's going to use a manifold absolute pressure sensor, okay, or a MAP sensor, and that's going to measure vacuum. The reason why we use a MAP sensor, under high load, right, we have low vacuum. So when the PCM sees low vacuum at a MAP sensor, it knows the engine's under load. So what does it do? It adds fuel, right? And with the mass airflow, we're measuring the amount of volume of air flowing into the engine. So if the mass airflow sensor is incorrectly measuring the amount of air, then that's going to affect the air-fuel mixture, right? So that's why we have these two, and we need to understand how each one of these actually works. So we continue over here. Okay, the mass airflow. I like to talk about the one-to-one rule. This rule works very well, even though a lot of instructors have said V6 3.0 or less, it's not as accurate. It's still a good starting point, okay? What the one-to-one rule is for every 1 liter of air, you should have 1 gram per second. So if I'm looking at a car that's a 5.3 liter, and I always bring this one up because we worked on one not too long ago, 5.3 liter engine. I plugged in my old Snap-on code reader, and I noticed mass airflow was reading 1.8 grams per second at idle. It's a 5.3 liter. I should have somewhere around 6 grams per second, right? And we ran a VE test, and it failed. Failed positive fuel trims, bad mass airflow. We replaced the bad mass airflow at that point, right? But if you can look at the mass airflow reading on a scan tool, it's going to give you a good idea, is this something I'm going to chase, right? Or if I'm going to move on to something else, okay? After we do that, look at your fuel trims. Fuel trims typically should be plus or minus 10%. Optimal would be about plus or minus 5%, okay? If you have a positive fuel trim, that means that it's compensating for a lean condition. If I have a negative fuel trim, that means it's compensating for a rich condition. This is important because this is where a lot of my technicians get screwed up. They see positive, so they think the car's running rich. No, okay? That's a rich command. The car's running lean, okay? It's the opposite. And if on the scan tool I see negative, that means it's a lean command because it is running rich. Okay, so that's where a lot of the techs get screwed up when they start seeing that information. Okay. It's the response. Yeah. So what you're seeing on your scan tool is not the actual condition. You're seeing the response to that particular condition. Okay. So that what you're looking at is the computer making an adjustment to be able to compensate for that lean condition, right? You got a vacuum leak, PCM picks that up. Your fuel trims begin to adjust to try to get rid of it, and then starts adding fuel to then get the air fuel mixture back where it needs to be, right? Okay. And I made up this chart. This is a pretty good chart because this helps us understand fuel trim. If you're dealing with a Nissan, for some reason, Nissan went alpha fuel trim. So 100 on alpha means 0% fuel trim adjustment. If I were to see 115 alpha on a Nissan, that means it's adding 15% fuel, okay? If I were to see somewhere along the way of 95, that means it's taking away 5% fuel, okay? That would be Nissan. Other than that, if I look at this on a generic or a general manner, plus 10% means that it's adding 10% fuel because the car's running lean, right? And if I see a car that's running negative 15%, it's taking away 15% because it's running rich. Okay, so it's making those adjustments to try to get you where you need to be, right? Mechanical and ignition system both passed your general test, so that only leaves fuel. So if we're checking for general system operation, and we already checked mechanical and ignition, the only thing we could check now is fuel, okay? Now, in order for us to check fuel, we can run some basic tests, look at sensor data, kind of get an idea. So what are some good sensor PIDs you guys would want to review to figure out what's going on with the car? Okay, so the question was, those last two bullet points, which would be those, do they apply to short-term and long-term fuel trim? Yes, they do. So anytime we're looking at plus fuel trim, either short-term or long-term, that means it's compensating for lean condition. Negative fuel trim, short-term or long-term fuel trim, then that means it's adapting for a rich condition. And then at the end was all OBD2 Nissans. Yes. So alpha fuel trim, you're going to see this on most Nissans nowadays. Typically, when I run any type of drivability diag, I don't know about you guys, but I always go generic with mine. So I'll go into the generic or global OBD2 or EOBD on the scan tool, and that's how I'm going to look at my data. Typically, when I'm there, that's when you start to see the alpha fuel trim, particularly on Nissan. Seeing this on Nissan and Infiniti, so that's why I'm making you guys aware of it. Okay. All right. So going back to the PIDs, what would be some good PIDs you would want to review if you think you have a fuel control problem? Fuel trim, short-term fuel trim. Okay. I had somebody say, what about injector pulse width? It's not a good indicator because what's the computer going to do if it has a fuel control problem? It's going to adapt, right? So that adjustment, you're going to look at your injector like, that thing's at 2 milliseconds, we're good. Well, no shit, PCM adapted for it. Okay, so you can't really look at that, but there's other values we could look at, O2 sensor, mass airflow, something of that sort. So we have MAF, idle air control count, short-term fuel trim, long-term fuel trim, O2 millivolts, and load. Yeah, those are good. Okay, so we could definitely look at those and kind of get an idea of where we're at, right? One thing I always do when I'm doing a diag, especially if I already ran some tests and I can't figure out what it is, I'm gonna look at scan tool data, right? But you want to narrow it down. Have you guys looked at some new cars? I've seen some cars with over 200 PIDs. Can you imagine trying to review 200 PIDs and trying to figure out what's wrong with the car? You can't. So narrow it down, okay? Usually I look at TPS, MAF, ECT, IAT, short-term, long-term fuel trim, O2 sensors if it has them, kind of get an idea of how this computer is running, right? Calculated load is another good one, and we'll talk about that in a bit when we talk about mass airflows. So here what we're looking at is we're looking at an oxygen sensor on a lab scope capture. Remember that a typical oxygen sensor, standard O2, which is a zirconia O2, has an operating range from 0 to 1 volt, right? 0 meaning lean, 1 volt meaning rich. Back in the old day, we used to look at cross counts. So we were looking at how many times the O2 sensor would go above and below 450 millivolts. And that gave us an idea of how good that O2 sensor was. When we're looking at an O2 sensor, we could do a number of tests. One would be raising the RPM to roughly about 2,000 RPM. And then at that point, your O2 should have a frequency of 1 to 3 hertz. So that means you should be cycling lean to rich 1 to 3 times per second at high speed. In California, if you're going to be an emissions technician, you need to know how to do a propane enrichment test. So that means you're going to use your oscilloscope connected to your O2 sensor, add propane. When you add propane, you're going to see your O2 sensor go rich. Once it goes rich, remove the propane. You're going to wait for it to drop back to lean. Once it's lean, whack the throttle wide open, and you're going to see your O2 sensor jump back up. Just pause your screen, measure your O2 from the lowest point to the highest point, and it should be switching not slower than 100 milliseconds, okay? So that O2 sensor switches slower than 100 milliseconds, you got a bad O2. It's lazy, okay? ECT for sure. Bad grounds on GM. Yep, 100%. Okay, so this right here is a propane enrichment test. Notice how we went lean. So propane was added here. Propane was turned off. Then the O2 sensor began to run lean. Once it ran lean, we did a wide open throttle test, and then we measured from the richest point to the leanest point, and that needs to be under 100 milliseconds. The two cursors on here don't have a measurement, but it should be under 100 milliseconds. Anything above that, then you got a lazy oxygen sensor. Okay. All right. The next thing we could do is, would you prefer to do fuel pressure or fuel volume? If you ask me, fuel volume. I've tested a lot of cars that passed pressure but had no volume coming out of them. Okay. That technique of fuel pressure has some problems. Fuel's coming up to the gauge and it's hitting the gauge, right? So the pressure is always going to look good, but what if I don't have enough fuel to actually feed all the cylinders? So for me, I always teach fuel volume. Now, the old school method was a non-modulated pump should give you 1 to 3 pints for every 30 seconds of cranking, right? That's the old school method. What we did is I worked with a couple of engineers and we developed this calculator. So if you go to this URL, I have a calculator on there. On that calculator, there's a URL, you click on it, and that's going to take you to a web page where you can select the year, make, model, engine size of the car you're working on, and it's going to tell you how many gallons per hour it moves. You punch that into the calculator, and then you tell the calculator what type of container you're using. Your typical water bottle is 500 milliliters, right? So then you punch in, for example, a 32 gallon per hour fuel pump fills up a 500 milliliter water bottle in 12 seconds. So if you're cranking it for 12 seconds and you don't fill up that water bottle, what does that tell you about the fuel pump? It's weak. So if your customer is complaining about, I have no power under load, right? Where's your problem? You got a bad pump, okay? Obviously, this is not going to work with modulated fuel pumps because modulated fuel pumps are going to modulate the voltage to the pump depending on driver command. So depending on your throttle actuation is how the fuel pump module is then going to turn that fuel pump to either create more pressure or less. So now when the car is at idle, what the computer does is it backs off fuel. So fuel pressure drops, so we're not creating excessive fuel pressure because we don't need it. We're at idle, right? But this is a good way for us to actually run that test. So this is where you'll find the calculators. This one goes directly to the fuel volume one, but there's a couple other calculators I have on there as well that you guys are free to use. Yeah. So they're asking if we could do a video on propane enrichment. We could definitely do that. I'll put that in my notes to get that going with you guys. So if we have a car that you think might have a restricted exhaust, one of the ways you could kind of point yourself in that direction, take the car on the road, get to a stoplight, and then just gun it, wide open throttle. If you feel that car go, whoa, slowly start taking off, more than likely it's exhaust restriction. Then when you get to the next stoplight, apply light throttle, and if the car starts responding normally, then you know for sure it's going to be restricted exhaust, right? We can also use our vacuum gauge, like that snap test we talked about earlier, or we can do an in-cylinder like we're doing here in this diagram or in this waveform here. This flat part or this plateau, this is your exhaust plateau, which should be at 0 psi. Why? Because it's venting into atmospheric pressure. If you see that plateau begin to increase, that means it's building exhaust pressure. Typically what we do is we'll set up our scope to measure about 2 seconds per division, and then we're going to go ahead and bring the RPM up. If I bring the RPM up and I see a really dark representation about mid-center, I'll measure that. And if I have high PSI, more than roughly about 3 PSI, then I know I have an exhaust restriction at that point. So then we can condemn and we can see what side it is, right? We usually run this whenever we have a car that has more than one bank and we think it has an exhaust restriction. We'll go one on each side. The one that gives us the elevated plateau, that's the one that we know has a restricted exhaust. Then at that point, we can start narrowing it down to what cat it is, right? The other thing we actually do too to kind of narrow it down is using a thermal imager. When you have a bad cat, usually a thermal shows that a cat's colder than the good firing cat. So that's another way that you guys can verify it. We did one not too long ago. It was the rear cat that went out. Front one was roughly about 500 degrees with thermal imager. The rear one was about 200 and some change. So it was way colder. So that was what indicated we had a bad cat. Okay, any questions up to this point? You guys good? All right. So let's talk about emission systems real quick because they're going to be tested on that as well. First things first is the PCV. What problems would you see if you have a bad PCV system? Rich condition, lean condition. What do you guys think you'll see? So if we look at the PCV valve, it's connected to manifold vacuum. Do you guys agree? So because I'm at manifold vacuum, if I have a bad valve, is this going to apply vacuum to the whole crankcase? Yeah, right? So if I have vacuum throughout the whole crankcase, is that going to create a really, really bad lean condition? Yeah. Okay. Why? Because all we're doing is we're just sucking all this out of the actual engine, bringing it back into the combustion chamber itself. Okay. So here's some of the codes. Oh, crap. It's not there anymore. Well, you might see a 171 or a PO 101 or a 500 erratic idle. Okay. So a lot of times you'll see stuff like that. Yes, sir.
How do you check if the PCV valve is in working condition?
So the old school ones, you take them out and shake it. And then with the engine on, you should have vacuum at the bottom of it. So that means it's working. The new ones that are diaphragm type, a manometer is going to be your best bet. Or like I did with propane. Just watching your short-term fuel trim, apply propane. If your fuel trim starts taking away fuel, then you know that they're interconnected. So your PCV took a shit at that point. Okay. The other way of doing it would be with a delta pressure sensor and using an oscilloscope, but that's a little bit more tech savvy. So you kind of have to already be using a scope, be comfortable with it to be actually tested. Okay. So evap. From here, we had the non-enhanced evap system. What non-enhanced means is it didn't check for leaks. It only checked for purge flow. So if you guys get a question on evap on a non-enhanced evap system, this system is real basic. So what we got here is first we got a solenoid. This electrical solenoid is going to be our purge valve, okay, which is that bad boy right there. Behind that, you're going to have a flow switch, okay? That flow switch then connects to your canister, and your canister connects to your gas tank. Whenever this purge valve opens up, vacuum flows through the purge valve, opens the flow switch and then starts pulling all the vapors out of the charcoal canister. This flow switch opening electrically signals to the PCM that there's flow. Okay, so that's how the computer knows it's flowing. How did the computer verify it though? What sensor is the computer going to look at to see if those raw fuel vapors actually made it into the combustion chamber? Would you think O2 maybe? Because if we look at it, we got raw fuel vapors leaving the charcoal canister flowing back into the engine. If those raw fuel vapors end up being burned off, isn't that going to reflect on the O2 sensor? So the PCM is going to check that flow switch. Flow switch says, hey, there's flow. PCM says, cool. Let me double check to make sure you actually flowed and there's no leaks in between the switch and the actual throttle plate. What does it do? Looks at the O2. If the O2 went rich, what does the computer know? We had flow and it made it into the engine. Okay. So what would happen if you're looking at a non-enhanced evap system and you got a lazy O2? Can that give you a code for no flow based off of the computer saying, all right, well, the switch opened, but I didn't see the O2 sensor pick it up? Okay, so if I have a lazy O2 here, the PCM is going to say, all right, cool, well, this switch detected flow, the flow switch, but O2 sensor didn't pick it up. But that could be because you got a lazy O2. Okay. The next system we're looking at, this is a vacuum decay enhanced evap system. What vacuum decay means is that we're looking at, or we're applying vacuum to the system, and we're going to look at the fuel tank pressure sensor. So this evap system was used for years. We had a purge valve, we had a vent solenoid, and a fuel tank pressure sensor on the actual tank. The purge solenoid, we usually call it the front door. Why? Because it's closed, right? Hopefully at home you keep your front door closed. There's some crazy ass people out there. So your front door is usually closed. Purge solenoid is usually closed. The only time we open it is when we're purging the system or to apply vacuum into the gas tank to check it for leaks. Okay. The vent solenoid is the back door. This one's typically open. The only time we close the vent solenoid is when we're going to seal the system and check it for leaks. So this is why the vent solenoid can usually be your problem or your headache child, because it's always open. So it could get dirt in there, rocks in there, mud, cockroaches, spiders, all kinds of crazy shit. Okay. Why? Again, because it's open. So then when we command it closed, if there's a spider in there, it's not going to close. So you're going to get a large leak. Okay. Then, again, the fuel tank pressure sensor. This is an absolute sensor. So the fuel tank pressure sensor is no different than a map sensor. Works the same. The only thing here is it's located on the gas tank. What the PCM is going to do is it's going to close the vent solenoid, apply vacuum to the gas tank, and then close the purge solenoid. Over time, it's going to monitor the fuel tank pressure sensor. If fuel tank pressure begins to drop off, then that's how it knows it has a leak, right? And if it doesn't, and it holds it for X amount of a predetermined period, then we know there's no leaks. It passes, sets the monitor, and goes on its way. But if for some reason on a vacuum decay, we apply vacuum to it and the fuel tank pressure sensor begins to see a drop in pressure, or excuse me, a rise in pressure because vacuum's dissipating, then the PCM knows I got a leak. Depending on how much pressure change over how much time you have, that's how the computer knows how large or small that leak is. Okay, so that's how this evap system works. Really simple. Okay, the next one we're going to be talking about is the EGR valve, exhaust gas recirculation. Whenever you see an EGR valve, what emission should you start remembering when we talk about an EGR? NOx. So anytime you see an EGR valve, you think NOx. Okay. What the EGR valve is going to do is it's going to open up and it's going to allow exhaust gases to flow back into the intake where it's an inert gas. So it's going to use up some of the volume in the combustion chamber and help us reduce the internal combustion chamber temperature. Over 2,500 degrees Fahrenheit, we lose control of NOx. So the EGR's responsibilities are going to help us cool down the combustion chamber just enough where we're not producing that much NOx. Okay. There's different style types of EGRs. we have a negative back pressure EGR and a positive back pressure EGR. A negative back pressure EGR, the key word is negative. Negative is letting you know that you have vacuum being applied to the top side of the diaphragm. That's going to lift the diaphragm up and then allow the exhaust gases to flow into the intake. The other style was a positive back pressure, and these I hated and I still do to this day, because these you can only test by increasing exhaust back pressure. So what you needed to do is you use the mirror and a flashlight in a certain position, watching the diaphragm, and have somebody raise the RPM. You bring the RPM three grand, and then you're looking for that diaphragm to begin to lift. If it begins to lift, it works. Okay. Now, if I apply vacuum to a negative back pressure EGR, I'm expecting that engine to stumble or die at idle, right? Because I leaned it out so much, the computer couldn't adapt to it, so it dies. Okay. If I apply vacuum to it and it dies, it works. Okay. So that's a good way for us to check it. We also have a different style EGR. The new ones are digital EGRs. These are going to be electronically controlled. So it's an EGR with a solenoid on top. PCM is going to be looking for specific sensor values to be able to turn that on and turn it off. Typically, when you have an EGR that's electronically controlled, the PCM is going to be looking at wheel speed. If you don't have wheel speed, then it's probably not going to be operational. So it's always a good idea to look at VSS or vehicle speed. If you don't have that, then that's probably why the EGR is not operational. So we got a question here. Fuel tank pressure on a scan tool is measured in voltage. In some cases, yes, it is. NOx, yep. And then which one is positive EGR, which one's negative? So looking at these right here, the one on the left-hand side is our positive back pressure EGR, and then this one's our negative pressure over here on the right. Okay, so the one on the left is going to be using exhaust back pressure here to lift the diaphragm and then allow the exhaust gases to go right through. Okay. The next one would be air injection. When we have air injection system, this means that the car needs that extra amount of air to get that cat nice and warm, so then we can start getting HC and CO to drop on a cold start. So the air injection pump is going to be electronic, usually runs for about 60 seconds at cold startup. Then what we're going to have here, this is a secondary air valve, and then this is our electronic switch. The electronic switch turns on this valve, allows oxygen downstream, goes into the exhaust, and starts converting emissions a lot sooner. Okay. All right. Let's talk a little bit about some computer sensors and switches before we finish this out. So this right here is what I want you guys to memorize, because you're going to need this not only for the test, but you're going to need this in real life. Whenever you're doing a data pit analysis or you're looking at live data, always start with this. Throttle position sensor, about 0.5 volt to 900 millivolts. Mass airflow, use the 1-to-1 rule. If it's a map sensor, typically about 1 volt to 1.3 volts. ECT, typically about 180 degrees or higher. Short-term fuel trim, you want to see be about plus or minus 10%, or alpha 90 to 110. Long-term fuel trim would be about the same. Lambda, about 1.0. O2 sensor should be above and below 450 millivolts. And then if sensor 2, okay, should be a steady voltage. Okay, and that's letting you know that you have a good cat. If you have a matching rear to front O2, you got a bad cat. So it's pretty simple, right? These are the data pits I analyze anytime I'm going to diagnose a car. Why? Because I can see a lot of information off of this that might help me with my drivability concern. Okay, so this is a good way for us to start. Plus, during the ASE A8 and L1, they're going to give you live data like this. And you got to pick out which one's bad. Okay, so this is why I gave this to you guys, so you guys could see it. And by being able to see this, then it's going to help you guys really understand how we should be looking at it. And then you'll be able to make a judgment call on what's going on with the car. Okay. All right, so throttle position sensor. This is a potentiometer. The way a throttle position sensor works, it has 3 wires. What are the 3 wires to any 3-wire sensor? Should be power, ground, and signal return, right? So if we look at this throttle position sensor here, I got a 5-volt reference, I got a throttle position signal or signal return, and a ground. Based off of this position, it's going to vary a resistance. Based off of that resistance change, we're going to have a voltage drop. So the PCM is going to be looking at that, and that's how it's going to determine position based off of the voltage reading. Okay, so like I told you guys earlier, a TPS should be about 0.5 volt to 0.9 volt. I fixed a Mitsubishi not too long ago where they couldn't set the EGR monitor on it. Okay. When they brought it to me, first thing I did is I plugged in my scan tool. What I noticed, key on, engine off, TPS was 1.2 volts. So the PCM saw it as 1.2 at idle, right? So what did the PCM see it? I was giving it gas. So because the TPS was off, it wouldn't fall into the right load and speed cell. So if that was off, that measurement was off, everything else was off, so it would never enter the right criteria to run the EGR monitor. All I did was loosen up the screws, bring it down to about 700 millivolts, tighten it up, and I went about 1.5 miles and I set the monitor. Okay, so looking at that data is what really gives you the idea of what's really wrong with this stupid thing. Okay, so just being able to look at those numbers, you're going to have an idea of where you're at. All right. Here we have an oscilloscope, and notice how we're applying voltage. So this means voltage is going up. I'm opening the throttle. And does the computer know whether I let go of the throttle here or if there's a bad sensor? Can it tell the difference? The computer can't tell the difference between you letting go of the throttle or an actual glitch. So that drop out there, what the computer does, it says, oh shit, he let go of the throttle. So what does it do? Closes fuel injector pulse, backs off the timing, and the car falls on its face, right? As your customer begins to apply the throttle more, the car repicks itself back up, right? Adds fuel, just timing, and then the car takes off. I've seen, and I always talk about this case because this one really pissed me off. A lady had her car, they sold her a transmission. And when I got the car, the transmission shop's like, dude, we diagnosed that it was a bad trans. We tore the trans apart. There was nothing wrong with it. And the customer complaint felt like a transmission slip. So when we started checking it, we noticed that we were getting like that lack of power on acceleration. We scoped the TPS and we saw a glitch like this. The fix was a TPS. Okay, so that kind of stuff is very, very, very stupid important because that's going to help you guys really ID what's wrong with the car. We also fixed an F650 not too long ago where the customer's complaint was lack of power. The truck would go into limp mode, and it was a moving truck. And all we found was a bad APP, accelerated pedal. We put it on the lap scope, and we had one channel that would be good, which was APP2. APP1 would drop out, all of a sudden just come back up. At idle, APP1 would just start accelerating on its own. Voltage would just start going up, back down. That one came from the dealership. Dealer had replaced a throttle body on it, and they were recommending a mass airflow and fuel pump. So all I needed was an APP. Okay. Yes, sir.
How often do dealerships tend to get things wrong?
Lot.
Really?
Yeah, they got unlimited power part supply. So I know a couple people that work at the dealership, and the way they diag it, pull code, go to the parts department, get a part, throw it on. Did they fix it? No. Okay. Change another part. And sad to say, a lot of dealer techs are glorified parts changers.
Wow.
Yeah. There are some techs that do take the time to diag, but a lot of times the way the dealers pay diag, they don't want to diag it because you're only getting paid 0.3 of an hour to actually diag it. Yeah. Yeah. So it really sucks. Plus at the dealers, most of these techs get so into the habitual roundabout of common failures, right? So it's like, what's that car doing? This and that. What code does it have? That? Okay, I know what it needs. And yeah, it's like I fixed 15 of those in the last 2 weeks, so I know exactly what I need to replace, right? Versus us as a aftermarket shop, we get so many freaking cars that it's not always the same issue. But what I see with a lot of independent shops is they get into that habit of like, well, I fixed 3 Kias within the last 12 months, right? That had that problem. This Nissan has the same problem. It's like, no, it doesn't. Okay, so then that's when they fall into that trap because they try to go the dealer route and they're not dealer techs, right? Best diag, 99% of dealer techs are parts changers. Some of us got trained properly though. Yes, some dealer techs did. And then best diag techs are aftermarket, so that means you guys. And then what I said, dealerships are just stress. Yeah, unfortunately, yes. Some dealerships are just very, very, very stressful. This right here is an EGR from an old style Ford. What Ford did is they put a position sensor on the top. This position sensor is also a potentiometer. The only difference is this one's linear. What this one's going to measure is going to measure lift. Whenever that EGR was commanded on with a EVR, or electronic vacuum regulator from Ford, it would open up the EGR. Diaphragm would lift. As that diaphragm lift, that position sensor would vary in voltage. That's how the computer knew the EGR opened. Then PCM would look at O2 sensor. Did that O2 go lean? Because we're adding oxygen, right? If it goes lean, then the computer can confirm, cool, I had lift based off of the position sensor, and I had a lean condition based off of the exhaust going back into the intake. Okay, so that's how the computer is going to verify that. ECT, or engine coolant temp. This right here typically is an NTC, or a negative temperature coefficient. What that's going to mean is car's cold, high temp. Car warms up, car's cold, high voltage, car warms up, low voltage. A thermistor, this right here is a temperature sensor. It doesn't matter if it's intake air temperature, ECT, cabin temp, fuel temp, it's the same thing. A thermistor is a thermistor. The way this is going to work is you're going to have a 5-volt reference to the sensor. Based off of the temperature of the thermistor, there's going to be a voltage drop. Based off of that voltage drop, that's measured by this internal voltage signal here, or like a voltmeter inside the PCM. The computer sees that. Based off of the voltage drop created here, that's how the computer knows the temperature of whatever it's measuring. Okay, so that's how a thermistor works. And again, it doesn't matter where it's at. A thermistor is a thermistor. Okay, they all work the same. It creates a voltage drop based off of temperature. Okay, as we can see on this chart over here, we can see that the resistance value based off of the temperature is getting lower, right? So if I'm at about 50 degrees, that's going to put me somewhere about 20,000 ohms, right? And then that begins to drop off as it gets hotter. Okay, so just depending on the type of sensor you're dealing with. So this one right here, here's another diagram. As the engine's cold, you're roughly about 4.5 volts. As the engine begins to warm up, you're going to start to see the actual voltage begin to drop off. One thing that the ECTs, or coolant temperature sensor, is really important for is monitors. Time to temperature. We need to look at our time to temperature. So what that means is when I start the car up, we need to be incrementing about 0.5 degree per second. And we need to see that on a ramp. If I'm looking on my scan tool and I'm only looking at coolant temp and I'm seeing it in a staircase form, that means that I'm having a slow temperature rise. It needs to be smooth, right? If I'm having a staircase style, that's telling me time to temperature is not there. That could mean you're having a hell of a time setting a CAT monitor, an EGR monitor, something of that sort, because it's taking too long for that temperature to reach normal operating temp. The problem is most people say, well, I'm not getting a P0 128. Okay. Well, yeah, you might not get it yet because it hasn't failed enough before it falls out of the manufacturer threshold. Okay. Remember, the guys who engineer the cars write the software and say it needs to be within this range. If you're at the bottom of it or at the top of the range, you're still within range. So it's not going to set a code. That's what a lot of techs have a problem understanding. And then they're like, well, I don't have a code for it. That doesn't mean anything, right? There's a lot of times where you're going to have to diagnose a car where you have no codes. Okay, and that's what really makes a good diagnostician. When you do drivability diag without codes, symptom-based. Okay, that's where you're going to shine when you know how to diagnose during symptom-based. Okay, so let's see here. So we got a question saying that EGR valves are off at idle. Yes, if the EGR was on at idle, that would kill the engine, and then the engine would die off. Usually bad thermostats, yep. And doesn't mean it needs to have a code. Absolutely. I've seen a lot of cars with no codes, but they got failing components. The next one right here would be the fuel injector. So this is a fuel injector diagram, and we're looking at it on a waveform on an oscilloscope. Here we have our source voltage between A and B. When the computer turns on the injector, we're going to pull it to ground. Typically, when we see these waveforms, it looks like it's pulled all the way to zero, but it's not. Depending on the type of driver that we're using for that fuel injector, it could be either a MOSFET injector driver or a bipolar transistor. Depending on which one it is how many volts off of zero it's going to be. If it's a MOSFET style, it's 200 millivolts, 200 to 300. And if it's a standard transistor, it's about 700 millivolts. From there, from point B, we pull it down to zero. And then point C across, that's the amount of time or pulse width the injector is actually on. At point C, we release the injector, and then this extra kickback voltage from C to D, okay, this is the leftover energy from the coil of the injector, and then it comes back off and then goes over. Point D should be above 35 volts. So anytime an injector turns off, this needs to go above 35. If it doesn't clear 35, you have a bad injector. Okay, the coil windings of that injector is bad. One thing that we really can't see here is on this, let me see if I can get the stupid thing to point again. So coming down from D to E on that bend there should be a little nipple. So usually that nipple right here. So right here in this area, there should be a nipple. So you're going to see this come down and then it nipples and then it comes back off. That nipple is the injector pintle coming back to its seated spot. Okay, so we can see using a lap scope if that injector actually came back to its seated position. So it helps us a lot be able to understand that this injector mechanically open, right? This one right here with idle air control, I brought this up here because you might get a question on this. What question are they going to ask you? They usually ask, the car comes in, and the concern on this particular vehicle is that the car is idling and idle air control shows 0 counts or 0%. What 0% or 0 counts mean on an idle air control valve means that the PCM has commanded it fully closed. If the idle air control valve is fully closed, the car should be off, right? But if the car's still running with an idle air control valve fully closed, what kind of problem do you guys got? You got a vacuum leak, okay? So you want to look at your IAC count. Typically, an IAC count should be about 20, okay, 20%. But if you see 0 idle air control or IAC percentage or count, that means that it's fully closed. And if the engine's still running, you got a vacuum leak. Okay, and last I remember, there was a question like that on the ASE exam. So you guys want to remember that one. Right here is a quick chart from a manifold absolute pressure sensor. This is an AC Delco. This is for GM only. Don't try to use this chart for anything outside of GM. And I'm telling you this because we tried it. Me and my students tried this with a Toyota, and they do not match up. Okay, so don't try it. Whatever car you're dealing with, look up that specific information, right? I already tried it for you. So, and I tried it in a controlled environment. Imagine trying doing this shit with a customer's car, right? You call it, oh, it's a bad map. You put a new one in, it's like, holy shit, still the same. Like, no shit, fool, you're looking at a GM map sensor chart. So what we're looking at here, and I mapped it out here at the top, map sensor, fuel tank pressure or fuel rail pressure sensor is a what? Absolute sensor. It doesn't matter where it's at. It's the same type of sensor, right? So we can understand that no matter what it is, whether it's manifold absolute pressure, fuel tank pressure, or fuel rail pressure, it's an absolute sensor, right? We also use absolute sensors on AC systems, pressure. Okay, so these are all over cars nowadays. These are going to vary in voltage depending on the actual pressure within the system. So this is going to help us identify vacuum, positive pressure, right, or any changes within that system, okay? All right, so we've gone to the point of no return. Right now, we've covered everything that I feel you guys should know to be able to pass the ASE and help you guys on drivability. Next thing is I borrowed some questions from ASE. So let's go over them, and then that way we can kind of practice these questions, and then we'll call it a night. So for this first one, okay, looking at this diagram, an engine equipped with the ignition system shown above idles smoothly but misfires on acceleration. What could be the cause? So A, high resistance at W. Where's W? W is here. So W would be the fuse. If there was a fuse the problem, wouldn't that affect all coils? Okay. Oh shit, that's X. Sorry. W would be one coil, okay, which would be our ground control to coil number 3. That might be possible. An open at fuse X. If that fuse was open, all 4 coils would be dead. The car would not start, right? A short to ground at Y. Where's Y? If Y was there and I had a short to ground, that would blow the fuse, so then that would make all these coils off. An open at the crankshaft position sensor circuit. If my crankshaft position sensor was open, will the car run? No. So what's my best answer? A. Okay. So that's how you want to run these questions. Look at the question, look at your answers, and see if any of these make any plausible sense, right? Don't just jump right in and be like, oh, okay, it's A. No, well, are you sure? Right? Obviously, don't second guess yourself because you know the content. All you need to make sure is, does this really add up to what I'm seeing up here? Right? So let's go to the next one. While the engine is running, a technician pulls the PCV valve out of the valve cover and plugs the valve opening. There is no change in engine RPM. Technician A says the PCV valve is stuck in the open position. Technician B says that between the intake manifold and the PCV valve could be plugged. So when I remove a PCV valve, that should change engine RPM. If the engine RPM doesn't change, right? If it was stuck open, wouldn't that RPM be fluctuating up and down? Because it's basically a vacuum leak, right? And if it's not, right, if it's stuck open, but I'm seeing that the question says no change, is it stuck open? No. So then A, that tech is wrong. And then tech B says that there could be a restriction between the intake manifold and the PCV valve. That's possible, right? Because we didn't have an RPM change when I pulled the PCV valve out. So if there was no change, it's possible that it might be plugged up. It could also be the PCV valve, but that's not an option, right? What are two options? It's stuck open or the hose is plugged. I'm going to go with the hose that's plugged, right? And if we look at it, what's the answer? Plugged hose. Okay. So let's look at the next one. After the compression readings shown in the illustration were taken, a wet compression test was made. The second set of readings were almost the same as the first. When we do a wet compression test, we're adding oil to it. So we're checking to see if the piston rings are going to seal with that extra oil. After we did that, it was still the same thing. So technician A says that it could be a burned valve. Very possible, right? Because that's going to have zero effect whether I add oil or not. And tech B says that it could be a broken piston ring. If it was a broken piston ring, when I added oil, compression would have came up, right? So what's my best answer here? Tech A, okay? It's tech A. I don't know why the hell I highlighted B. Sorry. Blue smoke comes out of the exhaust tailpipe of a car. What does blue smoke indicate? Tech A says that that's a blocked cylinder head oil return passage could be the cause. Or Tech B says that a stuck open engine thermostat could be the cause. Think of it this way. What causes blue smoke? Fuel or oil? Which one of those answers has anything to do with oil? Tech A. See what I mean? Okay, so if you really look at the question and answer, you can kind of pick out what's good, what's bad just by reading it. Okay, and it's just like looking at an oscilloscope or a scan tool. We're looking at the data to give us an idea of what could be wrong with it, right? Let's go to the next one. So a vehicle is being diagnosed for poor fuel economy. Engine tests show a rich exhaust gas mixture. Technician A says that it could be a failed oxygen sensor. Could a failed O2 cause a rich condition? It's possible, right? Tech B says that a failed engine coolant temperature sensor could be the cause. If the engine coolant temperature sensor goes out, the engine computer defaults to excessive fuel. Because the computer thinks that if the engine's running colder, then that fuel is going to recondense or become liquid again before it enters the combustion chamber. So it needs to give it more, right? Would you guys agree that both techs are right? Okay. You see how we could piece that one together? Okay. And all it is we got to look at it, read the question, and then see if one or both of those techs are right. Okay. Or mostly right. Okay. Because obviously there's different answers we can have, but that's how we can apply it. So looking at number 6, a vacuum gauge is connected to the intake manifold of an engine. With the engine running at 2,000 RPM, the pointer on the gauge fluctuates rapidly between 10 and 22 inches of vacuum. Leaking intake manifold gasket, worn piston rings, worn valve guides, or a broken valve spring. So remember when we were talking about vacuum gauges, I told you if you raise the RPM and you got a bounce in the needle, right? What kind of problem was it? And I told you can also see this by doing secondary ignition analysis. So the best answer here would be broken valve spring. If the valve spring is broken at high speed, right, where valve's doing this relatively quickly with a broken valve spring, we're going to be bouncing in vacuum because that valve can't compensate because of the broken spring, right? Number 7, technician finds no spark and no injector pulse on a vehicle that will not start. What cause could be the failure? Mass airflow, crankshaft position sensor, throttle position sensor, or a fuel pump module. If it was a mass airflow, we would have spark and fuel, right? If it was the throttle position sensor, we'd have spark and fuel. If it was a fuel pump module, we would have spark, no fuel, right? So which one of these would give us the best option for our bang for our buck? Crankshaft position sensor.
Would that be because it can't sense the timing?
Exactly. So the PCM can't sense where we are with cam-crank correlation. So because of that, it can't fire it, right? Okay, so the PCM is going to be looking for that signal, especially on the crankshaft where it's looking for the TDC indicator. If it can't find it, then it doesn't know when to fire what cylinder. So if it doesn't know how to fire it, it won't fire, right? So I actually have a good case study on a Lexus that we worked on for a, they did a timing belt on it, and then after that car had no power. And they broke the reluctor wheel on the crank. Pretty cool. We found it with the scope. Number 8, engine with a return type fuel injection system has high fuel pressure at idle. Which of these could be the cause? So if we have a return type system, that means we have a fuel pressure regulator. Fuel pressure regulator is usually vacuum operated. When the fuel pressure regulator is at idle, right, it's going to have vacuum applied to it, so it's going to reduce the amount of pressure at the rail. At high speed, where we have less vacuum, we're going to increase the rail pressure, right? So let's look at these answers. A leaking fuel pump check valve. If the check valve was leaking on the fuel pump, we'd have low fuel pressure, right? Because pressure is going back into the tank. If I had a plugged fuel injector, right, can that cause high fuel pressure? Well, it's not firing, so we're going to remain pressure, right? So that's a possibility. High manifold vacuum. If I have high manifold vacuum, that means the car is at idle. So that means I'm applying vacuum to the diaphragm. All that fuel pressure is going back to the tank, right? That's not going to be it. And then low manifold vacuum. So if I have low vacuum, diaphragm is not opening, it's closed. So that means we're going to increase rail pressure, right? So what would be your best answer here? Manifold vacuum, okay? Next one. Which of these could cause a catalytic converter to overheat? A broken air pump drive belt. So if the air pump doesn't have a drive belt, it can't work. So if it can't work, it's not going to overheat the cat, right? A plugged canister purge vacuum hose. If the canister purge line is plugged, there can't be any flow of hydrocarbon. It's not going to overheat, right? A stuck closed EGR. If the EGR is stuck closed, there's no flow. If there's no flow, it's not going to affect the cat. So far, A, B, and C are, for lack of a better term, full of shit, right? And the last one would be a disconnected spark plug wire. If I'm not burning the air fuel mixture, I'm shooting raw fuel into a oxidation catalyst that's roughly about 1,500 degrees internal temp with oxygen and fuel. You're going to melt the shit out of it, right? So what's your best answer here? D. Okay. Any of these could cause an exhaust gas recirculation insufficient flow. Keyword, except, right? A, an exhaust leak. B, stuck open EGR. D,